Welcome again. This is Dr. Ali Mugable. And we're covering joint Gaussian random variables. In joint Gaussian random variables, we have two variables. So we start with the x-axis, which we'll denote with the red color, and we also have the y-axis, or the y other variable, which is referred to with blue. So for the first variable, for the x-axis, we have the mean, and we also have the variance. The other variable, y, it has a mean of y bar and variance sigma y squared. In addition to the information about the individual random variables, we need the relation between them, and that's reflected by the covariance. So the covariance would be rho times sigma x times sigma y, where rho is the correlation coefficient. So give me the information about the marginal Gaussian random variables, x and y, in terms of mean and variance. We also need the relation between them, which is reflected by the correlation coefficient or by the covariance. Now we can construct the jointly Gaussian random variable. And the joint PDF is shown here. It's very similar to the single variable, but now it's of course a bit more complicated. So we have a term for x in the exponent, term for y, and also there is this joint term. So you can see that rho appears here, appears there also. So the expression is a bit more complicated, but the principle remains the same. It's jointly Gaussian. The shape is shown here for the joint Gaussian. If you look from the x side, you get a Gaussian shape if you have a cut, or if you look from the other axis, then you have also a Gaussian distribution. Now note that when do we get this exponent to be equal to 0? This exponent is going to be 0 at the mean values of x bar and y bar. So then this exponent will give you 0, and x exponent raised to power 0 will be 1, and what remains is this coefficient. So at x bar, at this point, x bar, y bar, at this point specifically, we get the peak. This is the maximum. How much is the maximum? It equals to the following quantity. This is directly from the expression or the equation for the joint Gaussian random variable. So you can see here clearly that at this point here, which is x bar, y bar, which is the centroid of the distribution, we get the highest value, and this value would be just the multiplier of the exponent. Now if we draw a cut here, then we get something like this shape. We get an ellipse or a circle, and this could be tilted or rotated or otherwise, and that depends on the value of x bar, y bar, and the shape or the rotation will depend on the correlation coefficient. We'll see more about this in the coming slides. So the bivariate, bi means two, the bivariate Gaussian random variable with specific mean, variance, and correlation coefficient is demonstrated here. In the first diagram here, we have the Gaussian, the marginal Gaussian distribution, and we can see different examples. These were generated using MATLAB. There's a MATLAB demo about the bivariate Gaussian random variable. I advise you to refer to that and just run it. It's a demo, and then enjoy it. You can change the value of rho, the correlation coefficient. Of course, the higher the correlation coefficient, then we get more of an ellipse shape, and then it peaks like a line. And if we have the smaller the value, then it looks like a circle. We'll have more of cuts on these curves in the coming slides. But you need x, y, and the relation between them, and that will determine the final shape. Now, I'm sharing with you here on the left a MATLAB script where you can cut and paste from our slides. You can get slides from my personal website. And then we just would like to highlight that there is a command called surv-c that will help you to plot two-dimensional curves. You can try this on MATLAB, or even if you don't have MATLAB, you can try the Octave, which is a free version of similar version to MATLAB. Okay, so we have 3 examples here for the joint Gaussian distribution in 2D. You can think of this as the weight and height distribution of students. And what you see in the lower curves here in 3, we have 3 different, we have cuts on the curve. So can you guess what's the correlation coefficient between x and y? X is shown here in the x-axis and y is shown here in the y-axis for all the curves. Now once more, this is the point, the center will be x bar and y bar. And if the correlation coefficient is positive, you get things tilted. The relation between x and y seems to be proportional. If we have a minus correlation coefficient, then it means as you increase x, y tend to decrease. And of course, the third case where we have correlation close to 0. So we're saying that for these specific examples, the first one on the left is 0.5. It's positive clearly. The one in the middle is 0. And the one on the left is minus 0.75. Of course, the larger the value, we go from an ellipse to a line. So we have a circle, and then it becomes like an ellipse and shrinks. As we get to correlation of 1, we will get like a straight line. In random variable case, I'm writing optional study here because it's a basic extension of what we had for the bivariate example. We will need to be using vectors here, vector notation. We are subtracting the mean, so x is this vector of random variables. In red, the x bar is a vector of the averages of the different random variables. We're going to use the covariance matrix. So the covariance matrix, we're going to have n by n matrix, and that's going to have, in the diagonal, we're going to have the variance here. Remember that the definition of the covariance between two I and j, it's equal to the expected value of the first random variable minus its mean times the second random variable minus its mean. Of course, if we're finding the covariance of the vector with itself, then we get the variance here. And if I does not equal to j, we'll get the covariances. So this is how we write the n random variable equation in general. Remember that here we have Cx is the covariance matrix. We have the determinant of the covariance matrix. We also have the inverse of the covariance matrix here. Instead of writing it in the denominator, we're writing it this way. So there is a little bit difference in the notation, but we can also show that the general n random variable equation reduces to the bivariate if we substitute for the case of 2. And the covariance matrix will be given by the following. Remember, the diagonal are the variances. And the off diagonal will be the same 2 elements. They are C12, the covariance between 1 and 2, and then C2, 1. These are equivalent to each other. You should be able to find the inverse of a matrix, a 2 by 2 matrix, or at least 3 by 3 matrix. So please review your math, how to find the determinant. Then you multiply the diagonals, then minus this times that, and you get the expression here. And then, of course, if you want to find the inverse, one for the determinant, if you want to find the inverse, what you need to do is you're going to have a minus sign for the, just get rid of this. Okay, you will get a minus sign here, minus, and then we have 1 over these 2 elements to get the lower matrix. And that will give you the inverse matrix. You can review this in any math textbooks or any website. For now, I would assume that you know how to find a 2 by 2 inverse, a matrix inversion for 2 by 2 or 3 by 3. Of course, once the order of the matrix becomes large, we can use software or MATLAB, or we can spend more time to find it. For the special case of independent jointly Gaussian random variable, then we can write the marginal. I'm talking about the bivariate example. For the case of x, we have the following expression. This is just a normal Gaussian. For the case of y, we also have another Gaussian random variable. If they are independent, remember that the joint PDF of independent random variables equal to the product. And if we multiply, if rho equal to 0, if the correlation coefficient equal to 0, we'll find out that the joint PDF equal to the multiplication of the two. And of course, this is a special case. If you can use the bivariate, you can use the invariate. And if you substitute for rho equal to 0, you will end up with the same multiplication expression. Now, remember we said before that if you have independent random variables, you know that they are uncorrelated. But we cannot assume that independent uncorrelated give you independent. Only if you have Gaussian. So this is not true in general, but it's going to be true for Gaussian. Jointly Gaussian and uncorrelated will give you independence, will guarantee to you independence. Independence guarantees uncorrelation, but uncorrelated, we can say it's independent only if it is jointly Gaussian. And that will make things simple, because now if I say uncorrelated Gaussian, you know they are independent. If they are independent, they are uncorrelated. So it becomes both way only for the case of Gaussian. I mean, for the case of Gaussian, it's true. In general, it's not true. In the following slide, we will go over the special case of converting correlated Gaussian x and y to uncorrelated Gaussian y1, y2. To convert correlated to uncorrelated, there are lots of applications. Some systems are designed and optimized for uncorrelated random variables. So you might need to change your incoming signal or incoming variables before you process them. So we're saying that if we have correlated Gaussian, then the relation between them will be like an ellipse. Remember, it could be positive or it could be negative. So to make them uncorrelated, we need to rotate this. We need to project x and y. So we can come up with a linear transformation, y1 and y2. They are new random variables. They are represented in terms of x and y. They're multiplied by cosine theta and sine theta to get their projection on the x and y. So we're saying, we're having a minus sign here, by the way. So we're saying, what is this linear transformation that will guarantee to you that y1 and y2 are not correlated? So let's calculate the correlation between the covariance between y1 and y2. By definition, the covariance equals to the multiplication of the expected value minus their means. Okay, so if we open the bracket here and substitute, I'm keeping the colors so you can trace. All right, so we can trace here. The red signal here, or the red part of the curve, is substituted here. So I'm doing substitution for y1 minus y bar. So this is showing in red, and this guy is shown in purple color. Okay. With a little bit of organization, we can get the following. So if you open the brackets and do the calculation, you'll find out that the expected value of x minus x times x minus x, this would give you sigma x squared. And similarly for the case of y, it will give you sigma y squared. The cross multiplication will give you the covariance term. So if we organize them, we'll get in general 4 terms. So we have 2 terms here and then 2 terms here. 2 terms will result in the variance when you multiply x by x and y by y. And the cross terms will give you the covariance terms. So this should be straight algebra, straight math. Now, we would like this to be equal to 0 if you want them to be uncorrelated. So if we think about this for a little bit and use a little bit of math, we can get cosine and sine double the angle. And we got the following final expression. Remember that sine over cosine will give you 10. So the angle that makes this equal to 0, if you equate this equal to 0, and you solve for theta, you'll find out that theta equal to tan inverse of the following expression. So this expression is function of rho, sigma x, sigma y. Now give me any correlated Gaussian variables, sigma x, sigma y, and rho, and I'm going to multiply them, make a new transformation, come up with a new random variables y1 and y2, and those y1 and y2 will be uncorrelated. So all we need to know here is theta, the angle, which is now derived in the following expression. So we can do this with MATLAB, we can try this, generate random variables which are correlated, and then we'll find out that if we do the following transformation, we get uncorrelated Gaussian. And this is also true, this applies for Gaussian and now Gaussian. The application here, the transformation, the linear transformation, works. We did not assume it's Gaussian, we just execute the expressions. So it would work for Gaussian and non-Gaussian. Here is the summary of the previous slide. So this is the correlation coefficient between x and y. In terms of the correlation coefficient, we can come up with theta. And if we execute the transformation, we'll get uncorrelated. On the side here, you can see different figures here. Whenever we have a circle, it means that sigma x equal to sigma y. Okay? If rho equal to plus 1, then we'll have a pi over 4. Okay, the angle would be pi over 4, which means that there is direct relation between the two. Of course, if it is minus 1, we can also get the angle on the other direction. Okay, so plus or minus pi over 4. So, of course, we can have different shapes. It depends on what we are going to do. We can also do conditional BDF. The beauty about Gaussian is that the joint is Gaussian, the marginal is Gaussian, and also the conditional are going to be Gaussian. All right, so now let's move to the next slide. Some properties of joint Gaussian random variables. They are completely defined by the first and second moment, mean and variance, and covariance. Mean and variance if it's a single random variable. If you have joint, then we need also the covariance. This is a very beautiful property. If Gaussian is uncorrelated, we can guarantee statistical independence. And then for linear transformation of Gaussian random variables is also random Gaussian random variable. If you multiply, add, you just get another Gaussian random variable. So all you need to know is the mean, variance, and covariances. The marginal density of joint Gaussian is also, of course, Gaussian. And the conditional is also the conditional density function of invariant Gaussian random variable will also be jointly Gaussian. Now let's conclude this lesson with an example, a practice example. Please try this and share your answers in the note section. It says here statistically independent random variable x and y have respective means x bar equal to 1 and y bar equal to minus 1/2. So what's required? Well, we're also told that the second moment is for the x is equal to 4 and the second moment for the y is equal to 11 or 4. Another random variable is defined to be, so we have a transformation. This is not a linear transformation. And then it says here find sigma x squared, sigma y squared, the correlation between x and y, covariance x and y, w bar, the average of w, and correlation between w and y. This should be straightforward. So please start by finding sigma x squared. We know the relation between the second moment and the first moment. Find sigma y squared from the relation between y bar and y bar squared. And then Rxy is nothing but the expected value of x times y. Okay? And then, of course, remember that there is a keyword here in the question that if you think about, there is one word that will help you resolve all the problems. And the keyword is the independent. So they are independent, which means we know that they are uncorrelated, the covariance equal to 0. And we can use this to solve the problem. We can then ask for the covariance for y bar and for I, y, y. Please share all your answers. We have 1, 2, 3, 4, 5, 6 to be found. Then please write them down and share your answers, so we'll see whether we're getting them right or wrong. Thank you again. We'll see you in coming videos. Please share, and we'll see you again.